So before we formally define Newton's first law in our notes, I want to do some demos connected to seeing what Newton's first law is and what Newton was talking about with his first law, and also talk about a lot of misconceptions people have about the first law. So Newton's first law is the one that people most often sort of misremember or half remember, maybe from 9th grade or 6th grade science or from something that they've heard like in popular culture. One way that people sort of misremember it, or really they're only remembering part of it, is that objects in motion stay in motion. Well, that's not true, right? We know that's not true. Like if I have this object and I set it in motion, it stopped moving. And so obviously objects in motion don't always stay in motion. And that's okay. Newton's first law has a little bit more going on than that. Another way that people often misremember it is that they remember objects at rest stay at rest, and well, that's obviously not true either. This is at rest, and look, I can make it move, right? And so objects at rest don't always stay at rest. And that's okay as well, because that's not actually what the first law says. What Newton's first law says is that objects at rest tend to remain at rest, or they want to remain at rest, and they will remain at rest unless they are acted on by an unbalanced force. So remember, a force is a push or a pull, and so what Newton is saying is that this is at rest, and it will stay at rest unless something pushes or pulls on it, and that push or pull is not canceled out by something else. So for example, right now, gravity is actually pulling down on it, but it's not moving. And that's because the table is pushing back up on it. And they are pushing and pulling equally hard, so they are canceling each other out. In fact, if I push down on it, it still doesn't move because the table just pushes back up harder. And so now I'm pushing down, gravity's pulling down, but we're balanced out by the table, which is pushing up. And so as long as all the forces are balanced, it'll remain at rest. And of course, if there were no forces at all, if this was just like sitting in the middle of space, unaffected by any forces from anywhere, it would also stay at rest. But on Earth, usually whatever forces wind up being canceled out if something is at rest and stays at rest. And that's useful for our problem solving too. If you know something is at rest and it stays at rest, when we draw our free body diagrams, which show all the forces, we know that all of the forces have to cancel each other out. But of course, you can get something at rest to start moving. And you do that by applying an unbalanced force. So for example, if I push sideways on it, and there's nothing to cancel that force out, it will not stay at rest and it will start to move. And we call that property of the object to want to continue doing what it was doing, inertia. So inertia is just that the object wants to have a constant velocity. So it's at rest, it wants to stay at rest, that's what it's going to do. It wants nothing more in the universe than to have a constant velocity, and it will stay at constant velocity, in this case 0, unless something makes it move. And the way we make it move is by applying an unbalanced force, for example, by pushing sideways on it when something else is not pushing back. Of course, if the forces are balanced, it won't move. So if I push on it from both sides, it can stay at rest. That's fine. I can apply all the forces I want as long as they cancel each other out. So the other condition or the other part of the law is about things that are in motion. And this makes a little more sense. Remember what I said, that inertia is this tendency of objects to just want to have a constant velocity. If it's at rest, its velocity is 0. It wants to stay at a velocity of 0. It wants to stay at rest. If it's moving, what it wants to do more than anything else in the universe is to continue moving at the exact same velocity, which means it's going to keep going in the same speed, in the same direction. But it's got the same condition. It can only keep a constant velocity, just like it can only stay at rest. It can only stay moving with a constant velocity if there are no unbalanced forces. And so the reason we don't see that in everyday life very often is because of friction. When I slid this across the table, the problem is as it slides across the table, this puck really wants to have a constant velocity. It wants to keep going that way. It wants to keep going that way at a constant velocity, but it's rubbing against the surface of the table. And there is a force of friction between the table and this thing that is going to slow it down. There's going to be some friction from the table pushing backwards on our object, and there's nothing to cancel that out. There's nothing pushing it forward to cancel out the friction, and so friction winds up winning. It applies an unbalanced force, and it causes it to slow down. It causes it to not have a constant velocity. Now, there are ways that we could still make it go at a constant velocity. One is that since I know there's going to be some friction, I could just push on it. If I push on it with the exact same amount of force as friction, it'll go at a constant velocity. Let's see what that would look like. So here I'm going to push on it, and I'm pushing on it just as hard as friction is pushing back, and so it goes at a constant velocity. It's not going at a constant velocity because I'm pushing on it. It's going at a constant velocity because all of the things pushing on it are canceling each other out. And so in this case, friction and I are pushing equally hard. It goes at a constant velocity. It'll go at a constant velocity, though, if neither friction and I were pushing on it. And the way we can demonstrate that is this thing is actually a miniature hovercraft. It has a fan inside of it that if I turn on, blows a bunch of air out the bottom. And that'll cause it to break contact with the table. And if it's not touching the table, there can't be any friction. And so we're going to get a chance to see something that Newton knew had to be true, even though it's not something we see in our everyday lives very often. This is going to just slide across the table at a constant velocity with nothing at all pushing it forward, because we don't need anything to push something forward to make it go at a constant velocity. We just need there to also not be anything pushing backwards on it. So if I give it a push and make it go fast, it goes across the table at a constant velocity. If I push it slow, it goes across the table at a constant velocity. Because while that fan is on, there's no friction. And so we don't need anything to push it forward to make it go forward at a constant velocity. I have to push a little bit to get it going because it starts at rest. But once it's moving, I'm not touching it anymore. Nothing is pushing forward on it, and it just goes forward at a constant velocity on its own, because that's what every object in the universe will do if given the opportunity. It wants to move at a constant velocity, and it will, unless there's some unbalanced force that prevents it from going at a constant velocity. Newton's first law in full. Objects at rest want to remain at rest, and there will be another video where we actually have the notes on this, so you don't need to write this down. But just to make sure we're clear on all of the parts of Newton's first law. Objects at rest will remain at rest unless they're acted on by an unbalanced force. Objects in motion will remain in motion at a constant velocity, so they will move at a constant speed in a constant direction or in a straight line unless they're acted on by an unbalanced force. If you are okay thinking of both being at rest as having a constant velocity and moving in a straight line at a constant speed at a constant velocity, you can sort of condense it down to this idea that objects will always have a constant velocity unless they're acted